In the last video, we talked a little bit about magnetic forces on moving charges. So that's basically the the situation I've drawn up here. So you have some charge, plus q, moving with some velocity in a magnetic field. And so what we found was that the force on that charge, the Lorentz force, so to speak, was equal to q v cross b. Okay, so this is the force on this charge due to this magnetic field. And so for this particular situation where we, for instance, have the velocity moving in the plus x direction, and then the magnetic field is going to be directed along the plus z direction, using the right-hand rule, we could figure out what direction that's going to point in. So basically, if the velocity is in the x direction and the field is in the z direction, that means that the force on this charge should be either in the plus or minus y direction. And so using the right-hand rule, which we reviewed last time, basically taking x plus x cross z basically points in the minus y direction. So basically, if I was going to write this down, it would have magnitude minus q v b naught, and that would point in the j hat, in the minus j hat direction, which is why I have this minus here. Okay, so that's for an isolated charge. Now, in reality, most of the time we're going to be looking at magnetic fields acting on objects. They're not going to be charges moving through free space. The most common situation will be, in fact, instead of a charge moving through free space, it'll be charges flowing through a wire, right? So in that case, we have moving charges, but they're no longer just individual charges, zipping along. They're kind of all clustered inside a wire. So if we have a wire and the wire is carrying some current, let's say, so this is this green wire I've drawn here. So let's say it's carrying a current in the x direction. We want, and basically if we look inside this wire, we see lots of little charges moving with some velocity v inside. So, we would expect then, because the wire is made up of moving charges, that there likewise should be some force on this wire. Okay, so how do we calculate the force on this wire? All right, so this will be, the more common situation that will occur, in reality when we, actually deal with magnetic fields acting on objects. Usually it is on, current carrying wires. So for instance, if you look at a power transmission line, that's a situation where you might be interested on the magnetic forces on that because it is carrying, for instance, a lot of current. All right. So we want to know basically what the force on the wire is. So the way we can try to figure this out is just to basically say, okay, let's look at some very small section of this wire. All right, so I'm going to, look at this section here. So I'm going to kind of draw a little end caps or separating. This is sort of the section of the wire we're interested in. Let's say it has some length dl. Okay? And let's say the wire has some cross-sectional area A. That's basically the area of this little end cap here. Okay? So basically we can think of this as basically when we want to compute the force on the wire, let's basically just say, that should be, we would expect, so F, and let's just say on this little segment here, on segment DL, or I'll just be more general. So let's say F on the wire, and I'll get to F to DL in a sec. That's going to be basically equal to the sum of the force on all the charges moving charges inside the wire. Okay, summed over the wire. All right. So let's just start by thinking about one small segment of the wire. So now I'm going to go to DL. So let's say F on segment DL of the wire. And so that's going to be just equal to in DL, the charges in that little section of the wire. So that's going to be F charges in DL, right? Okay, so if, for instance, so let's say that each one of these charges in the wire has some charge Q, right? It's going to just be a sum of Q V cross B for each one of all the charges in DL. So I'll say sum over their I charges in DL. Okay. So all I've said is that, if we have a little segment of wire of length DL, the total force on it is just going to be the sum over all the charges inside that wire. Now, if this segment DL is relatively short, right, then we can basically treat the magnetic field as being constant over the entire wire. In this particular example, the magnetic field is constant, but even if it wasn't constant, even if it was changing as a function of x, for instance, if this segment was sufficiently small, we could treat just the magnetic field as being constant in that range, right? Also, since this segment is very short, we can basically treat all the velocities. So you can think of the velocities of these charges as basically flowing, down the wire. If the wire was windy, that velocity would change depending on where you were in the wire. But, let's say DL is quite short, so the velocity for each one of these charges is going to be parallel, okay? So in other words, I can just write this as, let's say Q V cross B, assuming that B is constant everywhere in the segment DL. V is going to be the same. We'll say it's going to be the same everywhere because I said this length is very short. Q is going to be the same for all of them. And so this is going to be times the total number. So this is the force per charge, right, times the number of charges in DL. And pardon my crappy handwriting. All right. So what is this, right? We want to know the number of charges in DL. So let's just assume, for starters, that there's some density of charges in the wire, right? So let's just say that there is the density of current carrying charges. So that's the density of moving charges. There's actually many more charges in here because there's lots of electrons that are bound to the atoms in here that don't move. We're not really interested in those. The density of the ones that are moving, we'll call that little n, okay? Little n. Okay, so the number of charges in length DL is going to be equal then to the density of charges, right, times the volume of this little cylindrical section. So that's going to be equal to the cross-sectional area, A, times the length of that section, DL. Okay, so that is going to be equal to so basically this is a density. So this is a number per volume, and this here is a volume. So that gives us a total number, okay? All right, so then what we have then, so I can write, I'm going to move this over here. So basically F on segment DL is going to be equal to, I'm going to bring this over here. So it's going to be equal to N times, or rewrite this here. So I'm going to bring this out into the front. Okay. So basically I'll have a A times dl. These are just scalars, so I can move them wherever I want. And then I'll have an N Q V cross B. And of course, remember, V cross B, it matters, that I have V in front of B. If it was B cross V, then it would be negative, right? Because the cross product is a non-commutative operation. It means that you can't swap B and V. All right. So, hopefully, this may look a little bit familiar to you. I'll assume it's not looking familiar, but one can hope. All right. So this quantity, the number of the density of charges times the charge per carrier times the velocity of the carrier, that is in fact the current density. Okay. So that's something that we learned about a couple weeks back when we were looking at currents, conductors and moving charges inside conductors. So that's our current density. All right. One thing that we learned about current density, which again, I hope you remember, is that the integral j dot dA is equal to I. Okay? So again, current density is a vector. I, current, is actually not a vector. Okay? I is just a scalar. So in this case, I is not a vector. I don't say I, even though it's going in the x direction, I don't say I, little I hat. It's just scalar I, but I can just say it's, I'll define it as flowing, for instance, from left to right in the wire. Okay? All right, so basically what I have here then is this quantity here, so I'm going to rewrite this. So I have a dl, and then I have a j times a, or that looks a little weird. I have an a, and then I have a j cross b. And, all right, so j times a, since this is a, uniform wire, basically j times the cross-sectional area a, that's basically this quantity j dot dA integral. So that's basically I. So this is basically our current I, okay? But it has a direction. But I just said earlier that the current is not a vector. So the way we're going to write this is going to be a little weird. Okay, so magnitude A times magnitude J is I. But we want this to still be a vector quantity. So the way I can actually kind of make this a vector quantity is I'm going to make dl a vector, right? So dl is just basically, a vector which is parallel to the length of that little tube that we're considering. So it's the path length here, right? Cross B. All right, so let me just explain, why I can do that. So again, the current density is a vector. The current density, J, is basically defined by the velocity of the particles that are moving along the wire, right? So basically my J is pointing in the direction of V. Now, since the charges are moving kind of along the wire, right? The charges are moving down the wire. V is going to be parallel to dl, right? So as long as I can define dl as basically being parallel to the wire at every point, I know the charges are always going to be flowing inside and parallel to the wire. And dl, therefore, is going to always be, parallel to J. So I can do this swap here. So I can basically define the vector dl as being parallel to J. So I get this quantity here. So basically, if I consider some very small segment of wire, F on some segment of wire dl is just going to be the current flowing in that little segment of wire dl cross B. Okay, so B is what the field is locally right at that point, dl. And then, the dl vector basically is pointing along the direction of the current, right? So in this case, if I swapped the direction of the current, so if the current was instead flowing right to left, my dl would point in the opposite direction, okay? So this is basically the force on a small segment of wire dl carrying a current I. In a field B. So let me just briefly recap what I did. So I said, okay, well, we're interested in knowing what the magnetic force is on a current carrying wire. We didn't know what that was initially, but we did know what the magnetic force was on a free charge moving in space, okay? So then what we said is that, well, if you look inside the wire, really what all that is just a bunch of charges, moving together. So it's basically just some collection of charges moving with some velocity v down the wire. So then the total force on some little segment of wire is just going to be equal to the sum of all the forces acting on all the moving charges in that little segment of wire, okay? So that's what I started writing down here. So the force on some segment dl, of length dl, is just going to be equal to the sum of all the little charges moving inside of it. So basically that's just this expression, qv cross b, summed over all the charges inside. Since that segment of wire is very short, we can just approximate the velocity in the field as being constant over that little segment of wire, so it's just qv cross b, times the total number of charges inside that wire, in that little segment of wire. So that's equal to the density of the charges inside the wire times the volume of that little segment, right? So what I found then is if I rewrote this equation, I had a quantity here which is nqv, which was our current density. That was multiplied by A, and we remember that J dot dA was I, the current. So actually what we could do is we could just rewrite this quantity in terms of the total current. So there's a J and an A, so that basically gives us an I. We still have to preserve the direction and the velocity, and we said that, well, we know that the charges inside the wire are going to be moving parallel to the wire. So as long as we know the direction of that little segment of wire, that's dl, then we know the velocity, right? So just dl cross b, okay? All right. And you might have wondered, well, where did the velocity go? So the velocity then got embedded inside the current density, which got then embedded inside the current I. Okay, so the magnitude of this vector v is kind of absorbed in I. The direction is basically absorbed in dl. So what happens if we don't have a straight wire? So, what about, curved wire? Well, that expression that I just wrote up there is independent. This one here is independent of whether or not the wire is straight or curved, because it's only considering some tiny little section dl. So let me just set up this drawing here. So there's really nothing different about this situation than what I just talked about earlier. So here, so one thing to remember is that the current through this wire is constant, right? So one thing that we learned about current carrying conductors is that the current coming in one end is going to be equal to the current coming out the other end. And the current, let's say, coming in here is the same as the current there, there, there. Basically, just saying that if the current wasn't the same, that means that some charge has to be building up or has to be being depleted out of some part of the wire. And since we basically said that charge is conserved everywhere, that can't be the case. So the current basically through this wire has to be constant, has to have magnitude I everywhere, okay? Now the direction of the motion of the charges is going to be different, right? So, along this part of the wire, here the charges are moving this way. So, let's say DL is like this. Over here, right, the charges are going to be moving in a different direction, right? But it's still going to be parallel to the wire. So that's maybe some new segment DL prime, right? And so, this expression here works for every single point on here. You just have to keep in mind, right, if you're evaluating this at different points on the wire, you have to remember that DL, this direction, is going to be changing if the wire is curved, right? And then another thing is that B, the magnetic field, might be different on different points of this wire. Here I've drawn it so that it looks fairly constant everywhere, but you could imagine the field is doing something kind of funky, and maybe the field is pointing off in this direction over here, at which point when you want to evaluate the force on this part of the wire, you consider this DL prime segment and also what the field is at this point on the wire, right? If you're calculating what the force is on that point of the wire, then all you care about is the field at this point on the wire. That hopefully is pretty self-explanatory. All right, so now so let's imagine we have this whole, curved segment. And what we want to do now is to calculate the force on this entire segment, okay? So the force on the entire wire, or we want to know what the force is on the entire wire, not just on a small segment of it, right? Well, in that case, then what we're going to do is we're going to chop up this wire into lots of little segments, right? And so we can treat each one of these segments as being locally straight, right? So, I'm drawing what DL would be for each one of these little segments. And so, F total on this whole wire here, there might be, segments out here and here, but let's not worry about that. So we'll call this the total wire. Is just going to be equal to the integral over the whole wire, I DL cross B. Okay? And again, since I is actually going to be constant throughout the wire, we can even factor I out. So it's DL cross B over the whole wire. And so, if the wire has some funky shape like this, then DL cross B might not be so easy to evaluate because it's changing, in some funny way over the entire wire. But you could still evaluate it, numerically, for instance. You could break this up. If it's straight, we're going to do that in the sec. If it's straight, that's pretty easy. If it was a circle, that's also pretty easy to figure out. Okay, so let's calculate the force on some section of straight wire, let's say of length L. So I'll set that up. All right, so if we wanted to calculate now the force on, this straight length of wire of length L in this constant magnetic field, let's say it was carrying a current I in the X direction, and there was a perpendicular field in the plus, actually this should be the, we'll say that's the plus Z direction. My bad. All right, so in the plus Z direction, then we want to know, what is the total force on this wire? So we can use this integral that we wrote up here. So F total is going to be the integral over the whole wire. We know there is some current that's going to the right. dl cross B. All right. So I is a constant. We can factor that out. Oops. We break the wire up into little sections dl. Right. dl is just going to be parallel to dx. Since the wire is along the x direction. So I can just rewrite this now as dx, and that's in the I hat direction, cross vector b is b naught times the k hat direction, right? And now the integral, since I'm integrating over the whole wire, the integral will be from 0 to L. So I'm going to be integrating over dx from 0 to L. Now, I hat cross k hat, so if I use the right hand rule, I hat x cross z points basically out of the screen. So that's going to be, this cross means y is into the screen, so that's going to be in the minus y direction, okay? So, okay, so what I'm left with then is I get a constant b naught, which I can factor out. I have an I in front, which it's also been factored out already. I hat cross k hat gives me minus j hat. That's also a constant. So my integral is just from 0 to L dx. And that's a pretty easy integral to evaluate. That's just going to give me L, right? So in other words, F total on a straight wire, on this particular straight wire, is just going to be B naught times I times L, okay? And then it happens to be in the minus j hat direction, okay? So this is a general expression. So I'll pause this. So if I have a straight wire of length L and a constant and perpendicular field, the magnitude of the force is just going to be equal to the current times the length of the wire times the magnetic field. Okay? Now, if it was in a constant but non-perpendicular field, so let's imagine instead of pointing straight up, it was sort of pointing diagonally. Okay, so sort of like this. So let's say it had some x component as well as some z component. Then this form here would be a little bit more complicated. The magnitude then would then have to pick up the sine of the angle in between. So basically, when you take the cross product, basically we know that's the magnitude of the two vectors times the sine of the angle between the dl vector and the field. Okay? So this is a particularly simple example. I'm going to do a slightly harder one now. And so in your reading exercise, you're going to be encountered you're going to encounter a loop, a square loop, which is basically made up of 4 of these segments, okay? And so to calculate the net force on it, you basically want to consider the force on each one of these individual segments of wire, right? So since it's a loop, the current will be changing direction as you go through. That'll change the, when you take this dl cross B, since the current changes direction, you'll have to basically take into account which way the current is flowing through the wire. Okay. All right, so that was a particularly easy example. I'm going to do a slightly harder one now. I'm going to do the force on a straight wire in a spatially dependent field. Okay, so we still have the straight wire here, but now it's in some varying magnetic field. Okay, so the magnetic field, the way I've drawn it, is it's supposed to be getting weaker. So there's more field lines to the left and then less to the right. So basically the field here is stronger. The field here is dropping off the further to the right that we get. And so we'll call this end of the wire x equals 0. Oops. And we'll call this other end of the wire x is equal to L. And we'll say that the functional form of the magnetic field is basically some constant B naught over L plus X, okay? And I just wrote it this way so that the magnetic field at x equals 0 is not divergent. Because if I could have written it just B naught over X, but then the magnetic field here would be infinite. And I wanted to keep it finite, okay? So what that means is that at this end of the wire, the magnetic field is going to be B naught over L, because x is equal to 0. At this end of the wire, when x is equal to L, the magnetic field will be half what it was over here. So it'll like be B naught over 2L, right? So this is sort of meant to indicate the field is getting weaker as we go from left to right. So now if you want to know the total force on this wire, F total, right, I can just write exactly the same thing I did again on the left over here. So it's the same. It's I dl cross B. So we do the same drill where we basically just break up this straight wire into a lot of little sections, right? dl is going to just be dx. Or dx I hat, because the wire is along the x direction. So what I'm going to do now is I'm going to write, I can pull I out of the integral, and I'm going to still integrate from 0 to L, because that's still the whole length of the wire, right? dl is still going to be dx I hat, but now, instead of being a constant B naught, B will change. It'll be like B naught over L plus X. This is supposed to be a cross product K hat. All right. So there are certain things I can factor out here. So again, I cross K hat. So the magnetic field still at every one of these points, if I just took the cross product, dl is pointing to the right along the positive x direction. The magnetic field is pointing in the positive z direction, so the force is going to be in the minus j hat, in the minus y direction. So again, I can factor B naught I, and then the direction minus j hat. That unit vector is also a constant. And then I'm going to be left with an integral, but the integral is not going to just be dx anymore. It'll be a little more complicated, right? It'll be dx over L plus X. All right, but that's not so hard to solve. So we know that the integral of 1 over x is just log of x. So if I did a substitution of variables where, L plus x was u, du would also be dx. So basically the integral of this is just log of this quantity on the bottom. So I still have all the constants out here, minus j hat. And then the integral of this is log of L plus x evaluated at L and 0. So what that's going to give me, so that'll be, minus B naught I times j hat. And then log of, so up here I'd get log of 2L minus log of L when I put 0 in. So it's log of 2L minus log of L. Log of 2L minus log of L is the same as log of 2L over L, right? So the L's cancel, and so basically in this case F total would be equal to B naught I, and then now there is a log of 2. And that's a minus in the minus j direction. Oops, whoa. That's weird. In the minus j hat direction. Okay. One thing you'll notice here is that actually I lost my L. And the reason for that is that actually this here is B naught over L plus X. B naught actually then must have units of magnetic field times L, because, you know, if B naught had units of magnetic field, which I probably should have chosen a different constant instead of B naught. But, you know, this looks like a magnetic field, but, you know, if this was a magnetic field and I divided by a length, then B would be like magnetic field divided by meters or something. That'd be a weird unit. So this quantity here has to have units of magnetic fields times meters, because then if I divide by meters, I get magnetic field again. Okay, so in this case, B naught has, just so you're not confused, units of basically Tesla times meter. Tesla is the unit of magnetic field, right? All right. So that's how to calculate the force on a wire that's in a non-constant magnetic field, and then we'll do some more examples of this in lecture.